5.1 Part B. So we're going to continue to graph our sine and cosine functions, but today we're going to talk about the characteristics of y equals a sine of bx and y equals a cos of bx. So technically a and b, we've seen this before in the past, these represent some transformations, right? Technically a would be our vertical transformation or vertical stretch, and b would be our horizontal stretch, right? So just some review. The absolute value of a is going to be the vertical stretch factor on the graph by a factor of a. In terms of sinusoidal functions, we refer to a as also the amplitude of the function. So sometimes we're going to talk about it as a stretch, but sometimes we're going to talk about it as an amplitude. Okay, and so sometimes you can sketch a graph using transformations, or sometimes you can sketch the graph thinking about your period and amplitude. Okay, so it's kind of, you're going to have to kind of pick a method that works for you. I often go to amplitude and period, but that doesn't necessarily have to be the case. Okay, again, if a is negative, there's going to be a reflection in the x-axis. B, the absolute value of b, is the horizontal stretch factor on the graph by a factor of 1 over b. So this is still the same as we've seen in the past with our other functions. B is also relates to the period of the function. Okay, so how does the period b relate to the period? Well, to find the period of the function, if you take the original period of the base function of a sine or cosine function, which is 360 or 2 pi, and divide that by your b value, that will give you your period. Okay, so given the function y equals negative 4 cos of 2x from 0 to 2 pi, we're going to sketch the graph for at least one cycle. Okay, so the key here is we're going to use and then we want to talk about some characteristics of it. Okay, so the key here is we're going to start with the base function, y equals cos, which is what we kind of learned about yesterday. So some characteristics from yesterday is this base function, cos of x, has an amplitude of 1. It has a period of 2 pi in this case, because if you look at your x-axis, this is in radians. And the start point of my graph, so that's why start point is important, is at 0, 1. So I'm going to sketch my base function here. And I'm just going to draw it in a dotted line. Okay, so there's my base function. Okay, I just drew it in as a dotted line very lightly. Okay, and now what I'm going to do to this is I'm going to apply my transformations to it. So what do I need to do? I need to vertically stretch this by a factor of 4. So it's going to be stretched vertically by 4. I'm going to horizontally stretch this by 1/2. So it's going to condense, and then I'm going to reflect it. Okay, so what is going to happen to this graph? So I'm going to stretch it by 4 vertically, so this point is now going to occur there. Okay, and then I'm going to kind of take every one of these other points and I'm going to do the same thing. If I horizontally stretch this point, it's not going to move because my x value is 0. But now these other points I want to stretch by 4 vertically, but I also want to stretch it by 1/2 horizontally. So this point here, if I stretch it horizontally by 1/2, this point is going to be cut in half to there. Vertically, it's not going to change because my y value is 0. This point, I'm going to stretch it vertically by 4, so it's going to go to here. But I also need to stretch it by 1/2 horizontally. So that point's going to go here. So half of a pi is pi over 2. Stretch this vertically isn't going to change anything, but stretch this horizontally by 1/2 is going to go there. Stretch this vertically by 4, goes here. Horizontally by 1/2, so from 2 pi it should now be at pi. So I'm just going to draw one cycle of this. I don't need to draw. So I'm going to draw it a little bit thicker, but still a dotted line because this is not my final graph. Okay, so that is what my graph should look like after my stretches. So what's happened is I've physically taken these points, I've stretched them by 4. And I've taken these 2 points and I've stretched it by 1/2. So it should now be half the distance, right? This distance was once 2 pi in one cycle. It should now be half of that, which is 1 pi. Now I'm going to finally reflect this in the x-axis. So now I'm just going to reflect all these points. This point is going to occur here. That's going to stay the same. This point is going to go here. This is going to stay the same, and this point is going to go down here. So one cycle, my final graph should look like this. And then if you want to repeat it more than one time, right, I could repeat this cycle, and I could repeat it the other way as well. Okay, so that's what my graph would look like within this entire domain, right? Okay, determine the amplitude, the period, the max or minimum values, the x and y intercepts, the domain and range. Okay, and if you notice, this gives us a domain of 0 to 2 pi. Okay, so that kind of limits our domain right there. Okay, so let's talk about the amplitude. The amplitude is the distance from our central axis to our maximum point, so the amplitude is going to be 4. So it started at 1, it's now at 4. So if you notice, my a value, right, represents my amplitude. My period is now, how often does this repeat itself? Pi radians, right? Or, using this formula, I could have taken 2 pi and divided by my b value to get my period. Max and minimum values, fairly straightforward. Has a maximum at 4, a minimum at -4. X and y intercepts. So my x-intercepts, because I'm working in this domain, I'm going to ignore this part of the graph, right? I only want 0 to 2 pi. My x-intercepts are at, well, if this is half a pi, this is going to be a quarter pi, right? So it would be pi over 4. This would be 3/4 pi's, so 3 pi over 4. This would be 5 pi over 4. And 7 pi over 4 would be my x-intercepts. The y-intercept would be 0, -4. The domain, because it gave us the domain, is from 0 to 2 pi. And the range would now be -4 to 4. Okay, so characteristics of the function, sketch of my function, we're done. All right, Example 2, it says, given the graph below, state the period and amplitude, and then write the equation of the sine function. So we want this to be a sine function. Okay. All right, so how are we going to do this? So we're going to look at the graph. We are going to identify the period. So to figure out the period, I'm going to draw one cycle of my graph. Okay. So kind of tricky, this is at a half a pi, this is pi, so if I have 1, 2, 3 values between here and pi, that would make each of these a third of a pi. Okay. So depending on how many increment values you have between 0 and pi, that is your scale of the graph. So even though this says half a pi, that's not really helping me much. I want to look at the scale of this, right? Because I need to figure out one cycle, and one cycle ends up on one of these lines. So my period is 2 pi over 3. Okay. My amplitude, that's pretty easy, is 2. All right, so we can clearly see that the graph has been stretched both vertically and horizontally. Okay. So what we want to do is we want to think of this as either a stretch value, or we can think about our simple equation. A equals sine of bx. A is always your amplitude. B relates to the period. So to find the period, we can take 2 pi and divide it by b, or to find the b value, if you did the reverse, 2 pi divided by my period. So my amplitude is fairly straightforward. My amplitude is going to be 2. A is 2. My b value in this case, I am going to take my original period of my base sine function, which is 2 pi, and I am going to divide it by my period. So then I need to multiply by the reciprocal. So these end up canceling. So my b value is equal to 3. Okay, so my equation would be y equals 2 sine of 3x. But hold on. If I leave this as 2 sine of 3x, I know from my original base function that my sine graph normally looks like this. So it starts at 0, 0, which is the graph is still starting at 0, 0, but my graph originally starts by going in the upwards direction. In this case, it's starting in the downward direction. So this tells me that there has been a reflection in the x-axis. So instead of a positive 2, this needs to be a negative 2. Okay? Or you might also see that this could potentially, rather than reflecting this way, you could see this as a reflection this way. This point is now reflected to there. So, or you could see this as a reflection in the y-axis, which would make your equation 2 sine of negative 3x. So either of these equations would be completely right, okay, depending on what you see, whether you see a vertical reflection or you see this horizontal reflection. Okay. All right, and then finally example number 3. It says the graph represents the effects of tides on mean sea level over a 24-hour period. The graph has an equation of a cos of b of t, where t is in hours and h is the height in meters relative to the mean average sea level. Determine the equation of the graph. Okay. So this is talking about a cosine graph. Okay. Whenever we're talking about when we're comparing two things like time and height, these values have to be in radians. So the x-axis is in radians. Because remember, radian measure is just a number, where degree measure is an angle, right? And we can't relate angles to time in terms of our tides, right? So that's why radian measure is so important, is because it actually relates to a real life scenario. Radians is represented, can relate to time. It can relate to, I don't know, height. It can relate to anything in the world, where degrees can't. A degree has to be specific to the size of an angle. So in this question, again, the first thing we want to do is figure out the period of our graph and figure out the amplitude of our graph. Okay, so the period of our graph, if I were to draw one cycle, would be 12. And t is in hours, so this should be, so technically 12 hours is the period. The amplitude of the graph would be 4. And technically this is in meters, so 4 meters. Okay, so what would be the equation of our graph? So even though the period is 12 hours, if I want to write the equation, this is h of t, not just y, in this form, right? My a value is easy. That's just your amplitude. So a is 4. To find your b value, you need to go through this work. But because we're working in radians, we're going to take 2 pi and divide it by our period. So the b value in our equation needs to be a value of pi over 6. So our equation is going to be h of t is equal to 4 cos of pi over 6t. And technically that could or doesn't have to be in brackets, but you want to recognize that this is being multiplied by t before you're taking the cos of that expression. Okay, so then the next thing you should look at is there a reflection happening at all? So what we want to do is we want to think of our original cosine function, and our original cosine function starts on the y-axis and drops. So it looks like this, right? So has this starting position changed at all? No, it's been stretched vertically by 4, but it hasn't reflected it at all. So there's no reflection here, so we don't have to worry about that. So this would be our final answer and equation. Okay, so that is the basis of stretches and amplitudes and periods with sine and cosine functions.